that's what I was just explaining. The central ingredients will be two things. One is a tool known as the Dirichlet Neumann Map, which I'm going to introduce and explain why it's useful, and then a Pence decomposition. The central results that we will be exploiting in the algorithm is that, and again, this will be made more precise, the Dirichlet Neumann Map is a meromorphic family of of maps, which depends on a parameter, and this parameter, gives the Dirichlet eigenvalues at the poles of the meromorphic function. And so what we will be doing is we will start with the surface, we will decompose it into pairs of pants, compute on those pairs of pants, and then glue things back together. And so this is kind of these two aspects are what's novel about this method, because they give us some, great flexibility into the sort of surfaces that we can compute and what sort of things we can do. So for now, I've been very vague, but let me be more precise into what we're trying to do. So we start with a compact, sorry, by the way, this is just the theory before we get into the details. Hopefully this is review. So we start with a compact, smooth Riemannian manifold, and we are interested in the Laplacian on this. Knowing the eigenvalues and eigenfunctions of the Laplacian is hopefully clear that it's very important. It's a problem that's been studied a lot. It's useful for inverse problems, the heat equation, wave equation, Schrödinger equation, etc. They encode a wealth of information on the surface. So this operator, the Laplacian, is easy to work with, and we will be interested in what is known as the Dirichlet extension. So it's basically the Laplacian that is zero on the boundary. Sorry, the Laplacian whose eigenfunctions are zero on the boundary. And this is the key spectral theorem that tells us that the spectrum of this Laplacian, the Dirichlet Laplacian, is discrete. It has eigenvalues, which go up to infinity. And the key things for us is that each eigenfunction will be smooth, in fact, analytic for us, and real valued. So we can hope to compute them and see what they look like. And so the goal of this, hopefully with this little background, the goal of our algorithm is you give us a surface and it spits out both what these eigenvalues are and what the eigenfunctions look like. So this is, as you can see here, the sort of things that we'd like to see. You give us a surface in the hyperplane, and we've plotted here like the first three so actually the first three plots are one eigenvalue of multiplicity 3, and then here you have an eigenvalue, a higher frequency. So hopefully it's here. By the way, feel free to interrupt me and ask anything that might come up along the way. So as I was saying, the key ingredient will be this Dirichlet Neumann Map. It uses this key lemma, which is obtained through variational purposes. It's standard. So it's telling us that if you start with a lambda on the complex plane that is not an eigenvalue, then for any sufficiently smooth function, in this case h a half, on the boundary, this is the Sobolev space, there's a unique solution in the interior, which satisfies the eigenvalue equation and has those values on the boundary. This is, again, it's obtained through a variational problem. It's pretty standard. And here the trace, as a reminder, is the trace operator. So it's the restriction to the boundary, which is well defined. When the distributions are sufficiently well behaved. And so this lemma basically tells us, it gives us a map from the boundary to functions inside. So you take a lambda that is not an eigenvalue, and you obtain what is known as the Dirichlet Neumann Map, which basically goes from the function f on the boundary to a function on the interior. And now for that function with the interior u, you can see the normal derivative, the one pointing outward, and it basically gives us an operator from the boundary to the boundary itself. And so, this gives us this operator that I call big lambda lambda. And It's known as the Dirichlet Neumann Map. It's also very studied in physics because it's basically telling us, like, if I have a body and I put some sort of voltage on that surface, it's going to create a current in the interior, and that is, it's going to have an outward current, which we can measure. And so it's actually very studied in inverse problems, which try to reconstruct what the interior of the body looks like by just studying the voltage that we prescribe on it, and the measured effects on the surface without ever having to get to see the interior of that surface. So this is the graph of that operator, and I just want to make this point, which is important, is that even if you take lambda to be an eigenvalue, this graph is still defined, right? You still have a function in the interior, etc. The issue is that it's no longer an operator, because for a single value on the boundary, a single f, you can have different solutions inside, right? So if you take f to be 0, for instance, you can have the solution 0 inside, but also u an eigenvalue, non-zero, an eigenvector, and then you will have a multi-valued operator. It's not well defined, but the key is that you can still compute it. So programmatically, it's stable. We can do this thing, and even if we get close to eigenvalues, we're still able to calculate this Calderon range. And so what we're going to do is, this is what I mentioned was the meromorphic function family of operators that depend on lambda. We're going to calculate these Calderon ranges programmatically, and then at each lambda, when we get close to an eigenvalue, we will see that it will become multi-valued. So basically, we'll have a, our matrix will stop being invertible. That was one ingredient, the Dirichlet Neumann Map, and the other key ingredient is this Pence decomposition. So it's a theorem, given any surface of genus G, hyperbolic, we can decompose it into pairs of Pence. And so the key thing that we'll do is, instead of calculating the Calderon range or the Dirichlet Neumann Map on the entire surface at once, we'll do it on each pair of Pence and then glue these things back together. This gives us a lot of flexibility because, one, it means that we can reuse calculations. We can do a very high precision thing on one pair of Pence and then reuse that later when we build a surface from that. It also means that we can calculate all sorts of surfaces programmatically without having to ask the user to draw them in a sophisticated way, or give an equation that is that would be really not user friendly. So we place ourselves now on a single pair of Pence, and on this single pair of Pence, it will have 3 boundaries where the metric takes this form. The important thing and the Laplace-Beltrami operator obviously has an according expression in these coordinates. The important thing here will be that we can basically split solutions into each cylinder. So let me explain that better. We start on a pair of Pence and we get near a boundary. Near that boundary, obviously the pair of Pence looks like a cylinder. So our solutions have a Fourier decomposition into the angle variable. So if we just assume that U satisfies the Laplace operator on that near that boundary, we can decompose it as such. And then when we apply the Laplacian, we get an ODE. I don't find it particularly pretty, but the nice thing is that it only depends on R. We've removed the theta variable. And now this thing we can solve programmatically, either with ODE programs or using what we know about hypergeometric functions. It just so turns out that this fundamental system has fundamental system solutions with hypergeometric functions, and there's many implementation of these things online, which are great and we can reuse, and they've been optimized. So we've done something great here. We've taken a problem which was fairly complicated. The surface could be crazy. The Laplacian, how do you express that? And we've narrowed it down to just a cylinder with solutions that we know explicitly what they look like. We know even more. These solutions actually split into even and odd functions. So with these conditions at the boundary, these are basically going to represent the Dirichlet conditions and the normal conditions over here with the odd ones. And so then we decompose any solution not only on the Fourier basis, but in terms of this odd and even splits. And so our goal will be to construct, obviously, although we have the explicit solutions here, we can't take these infinite sums on a computer. We're limited by physics here. We construct a finite dimensional approximation of each of these subspaces. We do that by fixing a cutoff Fourier mode, and we say we'll only keep the modes lower than this. The nice thing, right, is that it converges exponentially in this cutoff. So we find that in the order, depends on what frequencies we're calculating, but in the order of 20, 25 modes is enough to get very nice results. And so once we have these solutions on, which I call V gamma 1, gamma 2, gamma 3 for each boundary of the pair of pens, the point is that we have 3 independent solutions which might not really be solutions on the entire pair of pens. They're just solutions around that boundary. And so what we do is we pick internal points on the hypersurface where we'll match the solutions. And so as I was saying all the way at the beginning, they're analytic. It's enough to just match them on these points. You can't see them here, but probably that well. But if you zoom in, they're very close together on a line. So hopefully that, the idea there was to also match the derivatives and such. The placement of these points was chosen kind of strategically based on what we know on the behavior of these hypergeometric functions, so that they don't happen at points where they're oscillating a lot and we miss the differences. I should have explained also that for these pair of pens, obviously, it's a 2D surface living in 3D. It's hard to work with that in a computer. So what we do instead is we work on these hexagons, which are half a pair of pens. So we take the pair of pens. Perhaps I can make a drawing like such, and this is one hexagon, which is half, because then I take another one and I glue it as such to give this pair of pens. So you'll excuse me for the drawing, I've done better, but this is the idea. And so here we pick points on these colors right here where we're going to be matching the solutions that we obtain on each independent boundary. Drawings. Right, so once we have these solutions, we match them. And obviously, programmatically, this is all done with matrices and such, and I spare you the actual calculations or the sizes of these matrices. But the nice thing that we can take advantage of is that the pair of pens has a reflection symmetry, which commutes actually with the Dirichlet Neumann operator. And so we can just work with cosines and sines separately, because effectively it's telling us that if we have an even solution on the boundary, the Dirichlet Neumann map will also map it to an even solution, and odd likewise. We don't need to mix these two things, and that speeds up the calculations. So if n is our number of modes, we obtain this matrix with the coefficients on this is the Calderon range. This is the matrix the graph that I presented at the beginning, but now in matrix form, split into odd, cosine and sine. And then from this, we obtain the actual Dirichlet Neumann map. This thing is not very well behaved on the bottom, because as I was explaining, when you have lambda very close to an eigenvalue, these things might not be invertible. And so this, it's nice to have when we're outside, but what will really be useful to find the eigenvalues themselves is the Calderon range. It's this first matrix. And yeah, so that's it for the algorithm. Obviously, I didn't go into given the time, into all the calculations and the matrices and so on. But the key thing to remember is that there's the Dirichlet Neumann Map tool, which is very useful in and of itself. And it's a great byproduct of our program, right? Because now we can use this for any other application that we want. And the pair of pens decomposition that allows us to glue things back together. just to give a concrete example of this in action, there's the Balza surface on which we've done the calculations. Background for everyone, the Balza surface is a Riemannian surface of genus 2 with the highest, basically like a lot of symmetries in them, so it's very nice to work with. It's been studied because it has a lot of nice properties, such as, you know, the biggest systole out of all the genus 2 surfaces. It's also conjectured to maximize the first positive eigenvalue. This is a lot of fun facts. It's not important for us, but it was just to introduce the surface. And we actually know a little bit about it. We know what the first eigenvalues are, which was great for us because it means we can check whether a program is really working. And that's why we picked this surface. And we also know about the dimension of the first few eigenspaces. We actually know that the first one, the non-trivial one, is dimensional 3, and the next one is dimension 4. So we could check whether that's indeed what we're getting. This is what we in red over here. So at the bottom you have lambda, which is the real parameter. It's the frequency that we're trying to test to see whether it's an eigenvalue or not. And then in red, the red bars over here, you can see it's where we know the first eigenvalues to be. And then what I'm plotting here is basically when we have that final matrix, the Calderon range, we can basically take the determinant, or in this case, the log of the determinant, and see when it becomes invertible or not. And so what we see here is that when obviously when the determinant goes to 0, the log of the determinant goes to -infinity. So at these poles, we're catching the derivatives, and you can see we get pretty good precision, at least in these first few, on where they are. The issue with this determinant thing is that we don't get the multiplicity. I guess you could extract it from the slope of this determinant, but if you, instead of looking at the determinant, look at the singular values, you can kind of get the multiplicity of that eigenspace, and we do that here. So here you have a plot, again, on the bottom you have lambda, you have the spectral parameter moving up, and then I've plotted here the smallest singular eigenvalues. So here, these are the ones corresponding to 0. If you come here to the first eigenvalue around 3.8, it's harder to see, but you basically have 3 lines coming in, the blue one, the orange, and the green one coming into 0. So that's telling us that it's multiplicity 3. And here you have 4 of them. You also have the red one coming to 0. So it's multiplicity 4. And so we did recover what we knew about these eigenvalues from a theoretical point of view. So that's it. Thank you very much. Just because this thing is this seminar is obviously very focused, this workshop is very focused on probability, I just want to say one word of that. People have been interested to use this to basically look at what is an average spectrum of a random surface. So if you generate a random surface, hyperbolic one, obviously, and you just look at its spectrum, what can you expect the first eigenvalue to be, for instance? There's many theoretical results on this, but for now, it's been very hard to actually look at these things and see what the eigenfunctions look like and so on. So that's sort of one application. But obviously, once you have the eigenvalues of the Laplacian, you can do all sorts of things in physics and as I described at the beginning, in inverse problems as well. So thank you very much. And if there's any questions, I'd be more than happy to take them.
Good. This is already a very good step forward. So thank you very much, Javier, for stepping in. My question is about your 10th slide. Can you please go back?
My which one?
10.
10.
Can you hear me well or not so much?
Yeah. I can hear perfectly. Let's see back.
Yeah, yes, this is it. No. Oh, excuse me. No, yes, this one. So can you please explain this step between the equation and the Gaussian hypergeometric function?
Yeah, of course. So the idea, right, is that because the Laplace-Beltrami operator takes this form, we can actually decompose things in these normal coordinates. So let me.
No, I understand it's the radial function, right?
Exactly. So this is just the radial function.
I don't see connection between this equation and hypergeometric equation.
So it just so happens that you can put this equation in the form of a hypergeometric.
So which change of variable?
Sorry.
Which change of variable?
Wow. It's if you change this, I have it on, I can send it to you. It's if you change this r into 1 over cosine, a hyperbolic cosine of r.
Okay.
Yeah. I can send it. I believe that I'm pretty sure that's the one, but there's a change of variables of this thing that puts it in basically the defining equation of a hypergeometric function.
Okay, perfect. Thank you very much.
Of course, if you mind, one comment on that. So actually, what happens with these hypergeometric functions in this regime, when you have a high lambda, which is about when you have lambda about so bigger than n squared. So n squared is the number of modes that I have. This radial function basically acts, is exponentially growing at the beginning. If this is 0,
right?
It's exponentially growing, and then the oscillations kick in. So it starts oscillating like this. And so what we're trying to do, the issue is that if you match here, it really explodes. Like I'm talking 10 to the 80. And so it's pretty, numerically, it's very unstable. So one thing we're working on now is trying to basically like find a more fundamental solution that we can kind of subtract off, if that makes sense.
By the way, what is connection between parameters A, B, C and lambda?
Oh, I have that explicitly. I can send it to you. It's not an easy connection, but I have it explicitly.
So, and in particular, this explosion of exponential function, how is it related to lambda?
It basically grows like e to the lambda over n squared. Obviously approximately.
Okay.
And it grows like this, and I mean you have an r here. Near and here. Once you're past a certain threshold, it's the exponential, the complex exponentials that kick in, so you start having the oscillation. There's obviously a very, I just didn't write it down because I found it's nasty formula, and so there was not much purpose. I didn't want to dwell too much on this, but there is an explicit dependence on ABC, on lambda, or L, etc. But yeah. So that's we're still like trying to make this algorithm even sturdier and stronger, like work on this hypergeometric solution, because obviously this is the only part where you have like actual work, the computer's actually working. The rest is just glue in matrices and doing things in smart ways that you don't have to overcompute.
Okay, perfect. Thank you very much.